present a parametric variational physics-informed neural network framework for rapid design exploration of thin slabs. This project is a result of collaboration between Dynzatec, Chalmers University, and Etteplan from Sweden. We have our co-author here as well. So I will start presenting. Slabs are mainly like horizontal load-bearing elements, and most of them, like they are, can be categorized as like thin slabs. What does it mean, thin slabs? That we don't worry that much about like if we have shear forces acting on those slabs. So in this case, we have something which is called Kirchhoff-Love theory, which is the most right mechanical theory to apply for bending dominated slabs. The shear is negligible in this theory, so we don't take care of the shear, we don't calculate the shear, and that will result in like kind of like smooth bending through the slab. So we can apply this with the finite element theory, but we have to implement like special elements, which they are very expensive computationally. So therefore, like many finite element analysis software, they don't use it. They use like another theory instead. But we will try to train a model here that using this theory. So if we look at the design optimization of thin slabs, mainly like we have this cycle. So like first of all, we start with initial design, we model it in the CAD. Then after the modeling, there's structural engineer who like meshing and so on. Then we have something which is called finite element method. So we have some software for this, and then evaluate the design and see if the criteria met, and then repeat this process again and again. This loop is a time-consuming loop, and it's the problem, not the solving is the problem. We solve, we can't solve, but this loop is very time-consuming. So therefore, we came up with like integrating the Kirchhoff theory into neural networks, and we looked first like at the simplest way of looking at Kirchhoff theory, which is like we have a clamped plate, and we have like uniform load on it, and then you can see here like we have an equation. Don't concentrate on the math here, but we can see that we have a big problem, which is the fourth order derivative. So like we have, and this will be very time consuming for GPUs to do this derivation always. And you need to do it like maybe like 50,000 times. So that will mainly result in a crash of any GPU that we have now. So we have another problem. The boundary condition here, as you can see, that we have the loss of the boundary condition. What does it mean? It means that the loss will never become zero, but we know that there should be zero. So, and this will result as well with loss balancing problems. So they will compete. The loss and the boundary condition, it will compete with the loss of the solution, and that will make the training longer, and you will not get accurate results. So, and we have vanishing gradients. The more that you have like a higher order, the more this phenomena that you will see when you train like a neural network. And that's the last one, which is spectral bias. So like we capture the smoothness of the bending in the slab, but we don't capture the bending on the boundary condition. And this is like a problem that we see. So to overcome this, we have three elements here. The first element is to consider the variational form of the equation, Kirchhoff equation. Don't concentrate on the math, but as you can see, we reduced the derivative order from 4 to 2. And this can be done by something called integration by parts, if you remember me. And then like we can use like a Gaussian injection into the test functions. So by using those, we will have kind of test function that we can use, and we reduce the order. The other thing, as I mentioned before, the loss. The loss will never, especially in the boundary condition I'm talking, the loss will never become zero. But we don't want it to be in the equation, so we don't want to present it. So we introduce something which is called R boundary constraint. And this is, we use very simple function, as you can see here, which is a map. And this function just calculates the distance from the borders to the center. That's it. This is the function. And we utilize this function by multiplying to the order of 2 because we want to assure, as I mentioned before, like we have clamp, so we don't have deflection on the boundary condition. We don't have zero bending in the boundary condition. By multiplying power to 2, like the ADF function, which is approximate distance function, by multiplying power to 2, so we assure that we have hard constraint of the EC, and we exclude them from the equation. The last one, which is hybrid spectral test space. So we utilize again the ADF function, but we will use the test functions, as you can see down here. But those functions are on the boundary; they are not zero. So we have to implement, like we have to force them to be zero. So we multiply them again by the ADF function. So this is the whole framework. First of all, we have like inputs here. We have training of a neural network. Then we have arbitrary deflection slab. But then we multiply the arbitrary deflection in the slab by the ADF function, power to 2. And we utilize as well like the test function, which is multiplied by the ADF function. And then we do automatic differentiation, which is like second order. So we do third or fourth order. And then we look at the residual and then the loss. And then we repeat this again and again. So that's the main framework of our project actually. So let's take one example here. We have an L-shaped plate, and we have like 2 parameters. This L shape will change. Just the lower leg will change, will be smaller, like shorter and thinner. So like we have like R1 and R2, they will control the length of the lower leg and the width of the lower. We have as well a corner, which is like a pivot corner. We consider that this is constant, 0.05 out of the whole. We use NLP, which is 6 hidden layers, 5 with 12 neurons, and we considered as well having step predictions. We utilized here self-scalable time as activation function, which is really good in this case. The first row is the solution from the exact solution that we calculate through finite software. The second row is the results from the model that we have trained. It's hard to detect that there is difference between them, but the columns. The first column, the second column, the third column. The third column is the error. And you can see that the error is concentrated like close to the corner, which is a problem that we will always see when we have such corners like this. Now, if to evaluate if we have like a good parametric model and we could train it like on the design space, because we had, as you remember, R1 and R2, which they have like a range between 1.2 to 1.6. So any plate that falls into this range, we want to have a solution. So here we chose like 16 validation cases, and we can see out of those validation cases, we have L2 error, which is 7.87%. And the maximum deflection, which is the decisive factor to decide if you will go with this slab or not. So we have maximum error of 5.9. 14 out of 16 cases, they have error below than 10%. So what does it cost, this one? It costs actually like 4 hours of a training, an NVIDIA A100, which is normal GPU. Yeah, I would consider it like everyone has access to it, like so. Yeah, but this time would be reduced drastically if you consider like H4 GPU or like you have many GPUs, so like parallelly. So I don't think if there's a company, it's a 4 hour, it's a factor, so they can reduce it drastically. Anyhow, you need 63 seconds to calculate this in using finite analysis. So based on the 4 hours and 63 seconds, you need to perform 230 queries, like to get benefit of this model. If you have like, if you just want to look at it once, I think like finite analysis is faster. But if you have like thousands of possibilities and you want to fetch the optimized one, then you will get like the benefit. And lastly, like here that we have, you can get the results after training by just like the zero latency, I would say, which is 0.08 seconds. That's perfect. So you train it once, you train like the whole model for all changes that they can happen in this geometrical changes here. So here what we have. So first of all, we could like use the variational form to reduce the order of derivative from fourth order to second order, and we could as well reduce the residual from 10 to 10 minus 6. So like the error is minimal in slab. We implemented the hard PC by using the ADF function, which resulted in good like results on the videos. The network shows like good results, I would say. So like we have 5.9% maximum reflection error, and the real-time design acceleration. So you don't need that much time to look at the results. You will get it after 0.015 seconds. So thank you for listening. And,